Okay, our next type of logarithmic equation to solve is when we have two logs of the same base equal to one another. We say that given log base b of m equals log base b of n, then we can drop the logs and immediately say that m is equal to n. We just have to make a note here that a table check is still required, just like in solving previous logarithmic equations. And we have to check anything that originally occurred inside of a log. So with that, let's go ahead and solve the natural log of x plus 2 minus the natural log of 4x plus 3 equals the natural log of 1 over x. To solve this, notice that we have 3 logs in this equation, but this process only works with 2. But we have a way to turn these 2 logs into 1 using condensing rules. We know that if we're subtracting 2 logs of the same base, we can condense this down with division inside of 1 log. So we can rewrite this problem as the natural log of x plus 2 divided by 4x plus 3. And that will equal the natural log of 1 over x. Now that we have 2 logs of the same base equal to one another, we can drop the logs and get x plus 2 over 4x plus 3 is equal to 1 over x. And now we can begin solving for x. We could either find the least common denominator between these 2 fractions and multiply it to each side, or we could just cross multiply, like so, which gives us x times x plus 2 is equal to 1 times 4x plus 3. And distributing in each case, we'll distribute the x to get x squared plus 2x is equal to 4x plus 1, as anything times 1 is just itself. And now this is a quadratic equation since we have this x squared here, so we're going to move everything to one side to get one side equal to 0. So we'll subtract 4x from each side of the equation and subtract 3 from each side of the equation. You can break these up as 2 different steps if you prefer. And this will give us x squared minus 2x minus 3 is equal to 0. And now we can go about solving this. Since it's equal to 0, we can factor and set each factor equal to 0. Or we can use the quadratic formula, whichever you're more comfortable with. In this case, I'm going to factor since it's a lot easier to just factor this. We get x, and now we need 2 numbers that multiply to give us negative 3, but add up to give us negative 2. So that would be negative 3 and positive 1. Negative 3 times positive 1 is negative 3. Negative 3 plus positive 1 is negative 2, and this will equal 0. And now we can take each of these factors, set them equal to 0, and solve. Remember, this technique requires one side equal to 0 to work. Now we'll add 3 to each side in the first equation to get x equals positive 3. We'll subtract 1 from each side in the second equation to get x equals negative 1. And it's tempting to just say these are our answers, but remember, we now have to do a table check. We're checking our x values of negative 1 and positive 3. And we're checking them inside of x plus 2 from here, 4x plus 3 from here, and 1 over x from here. So each of our original logs we take what was inside it, x plus 2, 4x plus 3, 1 over x, and we test our values in them. And when we do these table checks, it only has to fail one time. If it fails once, it is automatically not a solution. So when we take this negative 1 and we plug it into x plus 2, we get positive 1. That's greater than 0, so far it checks out. Now when we plug negative 1 into 4x plus 3, we get 4 times negative 1 is negative 4, plus 3 is negative 1. That is not greater than 0. It immediately fails. So x equals negative 1 is not actually a solution to this original problem. It fails the domain check. But now we can check x equals 3. When we plug 3 in, 3 plus 2 gives us 5. That is greater than 0, so it checks out. When we plug 3 into 4x plus 3, it gives us 4 times 3 is 12, plus 3 is 15, which is also greater than 0. And finally, when we plug 3 into 1 over x, we get 1/3, which is small, but still greater than 0. So x equals 3 checks out. And x equals 3 is our only solution. Remember, it is perfectly okay for a negative x value to be a solution. It's just when you plug it into the table, all of the resulting values must then be positive. Okay, with that, go ahead and take a minute to pause the video and see if you can solve log of 2x minus 1 equals log of x plus 3 plus log of 3. Okay, going through this, we have 2 logs on the right side of the equation. Remember, we can only do this if we have one log equal to another. So we must condense these like before. Log of x plus 3 plus log of 3, they are the same base, so we condense these with multiplication to get log of 2x minus 1 is equal to log of x plus 3 times 3 or 3 times x plus 3. Remember, with multiplication, you can write it in whichever order you prefer. And now if we distribute this 3, we'll get log of 2x minus 1 is equal to log of 3x plus 9. And at this point, we now have 2 logs equal to one another with the same base. This is technically base 10 since the log isn't showing. So we can now set the insides equal to one another to get 2x minus 1 is equal to 3x plus 9. And now we just solve for x. If we subtract 2x from each side, and then subtract 9 from each side, we'll be left with 1x is equal to negative 1 minus 9 is negative 10. But remember, before we circle this answer, we have to make sure that this checks out with our table. So we create a table with our x value of negative 10. We're testing it inside the original value of 2x minus 1 inside the first log, x plus 3 inside the second log. And while you can technically make another column for this log of 3, 3 will always be positive no matter what x is. So you don't have to do another check for that. It's automatically going to work for that log. But when we take this negative 10 and we plug it in to x here, we get 2 times negative 10 is negative 20, minus 1 is negative 21. That is not a positive number. It immediately fails, and that was our only possible solution. So since it failed, we say that there is no solution to this problem.